Okay, so you must be able to see my screen with the, yes, with the homework. So the lab about three-phase transformers is due today, okay? Today is March 8th, yes. And I have already uploaded homework 12 problems and homework 13Q questions. And those are about chapter 11, feeders. So then we have 3, 6, 8. I think there is one more question here. Okay. So then, let me see, which question is this? 25. There is one more question here. Fine. So this homework are due this weekend, all right? So 12 is Friday, and then March is, sorry, and the 13th is Saturday. And then next week is spring break. Fine. So let me now show you the, this is roster. So please write your name in chat. Okay. So then let's look at the, let me move out from here. And now let's look at the book. So chapter 11, we already started discussing about chapter 11. Continues, so here is the definition of ampacity. So let me show you this right here on my desk camera. Here on my desk camera, hold on. Okay, so these are the questions. So these are the questions for Friday or Saturday. This is here are the questions. Questions 2. So questions 2. What are the 3 separate requirements that can dictate the final selection of the conductor size for the feeder? Question 2. Now, if you look at here, is short circuit current rating, maximum allowed voltage drop, and number 1, continuous current rating. So there are 3 conditions that the feeder conductor must comply, all right? Current rating, which is the ampacity, the short circuit rating, and the voltage drop. And then here is problem 2, question 3 here. What's the definition of ampacity? Continuous current rating of conductors. So here is the definition of ampacity, okay? The current in amperes a conductor can carry continuously under the condition of use without exceeding the temperature rating of the conductor. So then the conductor, remember, is going to have three main characteristics. One is material, copper or aluminum. Number two is the gauge, the diameter, basically, the gauge, the circular area. And number three is the temperature rating of the conductor, which is given by the insulation. Okay. Question 10. Okay, for a three-phase, four-wire feeder, electric discharge type, lighting. Why must the neutral be considered a current carrying conductor? Okay. So look, in this tab, let me get a page. So we are in lecture 17, 16A. So today is 8/21, ELE 3371. So neutral is neutral conductor a current carrying conductor? Okay, so look, balance case, the answer is no. Unbalanced case or harmonics, the answer is yes. Okay. So why is this important? Let's see. We'll see. But let's explain why yes. The harmonic means the third harmonic. So then that means that we have, for example, a cosine 3 omega t. That's the first phase. Cosine 3 omega t plus minus 120. Cosine 3 omega t plus 120. So this is A, B, C. Okay. Under normal conditions, we have, without harmonics, no harmonics, we have cosine omega t minus 120, cosine omega t plus 120. Do the sum equals 0. We remember lab number 2. In lab number 2, we check that. So this is the normal condition. The neutral is carrying a current equal to 0. But right here, the sum is going to be equal to what? Look. So it's cosine 3 omega t plus cosine 3 omega t minus 3 times 120, 360, which is equal to cosine 3 omega t And then the last phase, 3 omega t plus 360, which is equal to cosine 3 omega t. So this is the sum. So the sum is not 0. The sum is equal to 3 times cosine omega t. See the difference here? So that's why for the balance case on the left, we got no. And for the unbalanced case on the right, we have yes. So then let's see. Let me, so then why is this important? Let me check the ampacity table. Okay, so page 343. Let me go to page 343 here on the okay, 343 right here. So here is this table. So look at the heading. Ampacities of not more than 3 single insulated. So this table is for 3 single insulated conductors. Okay, so then those 3 are called current carrying conductors, because there may be in the raceway other conductors which are not considered normally current carrying conductors, such as the grounding equipment conductor. Okay, so these tables for ampacity are good for 3 conductors. And then what happens if there are more than 3 conductors in the raceway? Then let's go to the next page 349. Okay, so here we have our 3 conductors in the raceway. The conductors are insulated. So that's the normal case. There may be another conductor, but then look at, this is the table that I wanted to show you. Adjustment factor for more than 3 conductors. Okay. Current conductors, current carrying conductors. So then if the neutral is not a current carrying conductor, the neutral will be within the conduit, but it will not be considered as a current carrying conductor. But if it is considered as a current carrying conductor, then the neutral will make the 4th conductor, and then we have an ampacity penalty of 80%. Okay, so we have factors: field factor, field correction factor. Okay, let me put here correction. And then we have the temperature correction factor. temperature correction factor, okay. And then we will have another, the continuous load correction factor. So we have A, B, C, temperature, and then continuous load correction factor. Okay. So then let's look at an examples. Example one. Look, so let's go and look at example one next. Right here. Example one. So we have three-phase, four wire, okay. 250 kcm, that M is for 1000, 75 degrees insulation, 3A, 40-degree temperature, feeding an incandescent lighting load, okay. Incandescent light load. So this one, no harmonics, okay? Okay. So the field, excuse me. So the field correction factor is equal 1 because there are only 3 conductors. Okay, next, the temperature correction factor. For ambient temperature, what is it, the ambient temperature now here? 40 degrees. What is it? So let's bring the table. Here's the table. Okay. So we need to look at the column of 75 degrees. So this is the 75 degrees. No, the second one. This is the 75 degrees. And then we go to the bottom, ampacity correction factors, temperature, 40. So this is this row, 3640, 0.88. So we have a correction factor of 0.88 here. Now, in this problem is looking at conductors 250 kcm. So scroll up on the same column, go to 250. Here is this is the row for the conductor, 250. So then the ampacity is 255. And the temperature correction factor is 0.88. So we have corrected ampacity equals ampacity times temperature correction factor times field correction factor times the other one, continuous load correction factor, okay? So then we said it was 255 amps times 0.88. And then all the other correction factors are 1. So 258 250 times, then we get that result, 224 amps. We are looking at example 1, okay? And then there is this comment, there is no need to derate for the neutral, the 4-wire, because there is no third harmonics. Now, example 1, 2. Now the ampacity is 380 amp because the conductor is thicker, 400 kcm. The neutral will be considered as a 4 current carrying conductors because of fluorescent lighting. Okay. So for example 2, what do we have? We have temperature correction factor equals 1 because it's rated at 30 degrees ambient temperature. Continuous load correction factor is equal to 1. Okay, well, it's not here yet, but we will talk about that later. We don't need this yet, okay?
Dr. Ramos.
Yeah.
So the fluorescent lighting that introduces harmonics, right?
Yes.
Oh, okay.
Fluorescent lighting introduces harmonics, yes. Because of the electronic ballast and also because of the
Discharge characteristic.
no, it's more on the magnetic core of the ballast because they have a series ballast in with the lighting, and then that ballast has a magnetic core, and magnetic cores introduce harmonics. But in this case, the film correction factor is, it says it should be considered a 4th conductor, a 4th conductor. So for the 4th conductor, it's 80%. 4th conductor. Okay. Okay. So then that's example 2. Then in example 3, aluminum conductors, 8 conductors, 45. Okay, 8 ALM conductors. 75, 45 degrees centigrade, ambient. So then we have temperature correction factor here, and then we have fuel correction factor here. So for fuel, if you look at the table, it is 70%. And for the temperature correction factor for aluminum, and then this is 75 centigrades. So now we need to look at aluminum here. Aluminum here, look. -45 centigrade. So it looks like 0.82, 0.82, okay. So then this is 0.82. And the ampacity of the, what is it? Number 6. Okay, so number 6, we were here in this column. Number 6 is right here. Right there. So it's 50 amps aluminum. But we will see the high impact. 50 amps. Look at the high impact. Correction ampacity. 50 times 0.7 times 0.82. Well, approximately 50 times 0.7 times 8, 56. So 20 amps, 28 amps. Híjole. See, it has a great impact. We were affected by 70% here and by temperature. Okay. So let me quickly show you a picture show. And then let's see if we can quickly find documents. Picture shows. My picture show. My picture selected. Okay. Building inspections here. Look at that. Can you see 4 conduits? And that's because there are several conduits, several conductors, and they are parallel conductors. Let me see if we can look at the better picture. See, apparently there are four conductors per phase. You see 4 conductors here?
Yes.
With orange?
Yeah.
And then on blue, there are 4 conductors per phase. So if we put them all together, we will have about 16 conductors in one conduit. And then for 16 conductors in one conduit, the field correction factor will be 70%. 70%. So there is a shortcut to do that. And that shortcut is to put 4 conduits. So this is called parallel conductors. So you have 4 conductors for A, 4 conductors for B, and 4 conductors for C. I cannot hear, sorry. Okay. So then we have 4 conduits And we are not looking at the neutrals here. Okay, so the rule is that you need to put in each conduit. Oh, this is red, sorry. You need to put in each conduit a complete set of the three phases. Rule, you do not put all A conductors in one conduit. No, you need to form a complete set. So for example, for the last conduit, we need one conductor C. We need one conductor B.
What's the reason for that?
For not putting them together.
Yeah.
Okay, the reason is that, okay, look, see, as we put them here, as now I'm showing, the net current within the conduit is 0. Okay, do you agree on that?
Yes.
So therefore, the magnetic field, H field created by that is 0. Now, if that is not the case, there is going to be a net magnetic field, and that magnetic field will be changing with time, and it will be inducing currents in the metal conduits around them. So the metal conduits are going to get hot. Okay.
Yeah, I would have never thought of that.
Well, that's the reason why you see this clumsy, or sorry for, I don't know if it's the proper noun or not, but they look, let me show you some other pictures here. Let's see, look at this. This, see, for example, here is some paralleling, but for example, this fuses, there are two conductors in parallel, two yellow, two red, and two blue. So then there are two conduits. There is a third conduit on the right, but that's not for these conductors. That looks like to be a conduit for some passing by conductors. See, here they look beautifully arranged so that the net is 0. The net current in the in each conduit will be 0. Okay, fine. So then let's look at another question like this. Okay, so then question 12, short circuit current rating of the conductors. So for short circuit current rating of conductors, then let's look at the book and then see what the book has to say about short circuit current rating. Conductor material, conductor. Okay, so then we go to page 352. Here it is. Okay, So the conductors, the feeders need to be calculated on basis of short circuit. Says here, resulting high short circuit currents can cause the conductor temperature to rise rapidly. The breakers require some finite time before it can detect and then fully interrupt the current, the fault current. Therefore, the feeder conductors must be sized large enough to carry the fault current for this time interval without reaching a temperature that will permanently damage the insulation. Okay. So then going back to chapter 3 or chapter 2, no, was it? I think it was chapter 7 when we discussed this. It's going to be an asymmetric current, which is a factor, K0, and the symmetric current. Symmetric current is the available short circuit current. K0 depends on the breaker and on the number of cycles. So here is the K0 factor, look. As we can see, the total clearing time in cycles. So we apply that. And then next, so from this table, we can look at how many cycles for clearing. So then we come to this plot. So the family of curves are for different cycles. Then we have the, on the horizontal, we have the size of the conductor. And then on the vertical, we have the short circuit current in thousands of amperes. Okay. So the idea is this. You have a software program to calculate the level of short circuit current. So, and then you can use the information about the conductor you are looking at, the gauge of the conductor on the horizontal. And then you look at this table, choose one of the plots and see where they intersect. For example, here I show one fuzzy halo here, which is 100,000 K for conductor 250 kcm. So this says this, conductor 250 kcm is able to withstand for one cycle, is able to withstand 100,000 amps. That's the rating of the conductor. So then those 100,000 amps, which is rating conductor, you compare with the calculation from the software program of the available short circuit current there. And then we will have an estimation of if the conductor is good or not. So this is, then we have another table I don't know what, okay. So here is the difference, look. So this is a different type of conductor. The insulation now is for XHHW. The first table was for the common conductor. THW is the common conductor, is thermoplastic. That's what the TH, no, the T stands for thermoplastic, the H for heat and then water. So T thermoplastic is not very good. For example, this type of conductors, yeah, you cannot use outdoors because the sun will destroy the insulation. The ultraviolet rays in sun destroy the insulation. However, these conductors, the XH, the X means cross link, and then it has HH, double heat, so more temperature rating of the insulation. Okay, so then these conductors have a stronger, durable insulation. Okay, and then one more for aluminum. See, aluminum here. So aluminum be softer for sure. It's not as sturdy as copper. So less short circuit current. Okay, so example 11.5. Determine the symmetrical short circuit current rating of a 250 MCM conductor thermoplastic insulation 408 volts. So that's the one we were looking here. So it says from figure 11.5. So here is figure 11.5. So then it says conductor is 250. So this is the conductor. Then how many cycles, or 2 cycles? So that's this point right here in the corner of the ruler. So then moving to the right, it's going to be 70,000 amps. And then it's affected by the K0, 1.3. That K0 is 1.3. So that depends on the circuit breaker, which is together in this case. So let's see here. 1.3 is a circuit breaker. Okay. So that's this example. So then there are different examples. See, look, the next is cross-link synthetic polymer type. So same conductor. Is it 250 MCM? Yes, 250 MCM, but now different insulation. So it can withstand higher short circuit current. Okay. So that's, and then the aluminum, again, same conductor, but then the current drops, the short circuit current drops by very quickly. Excuse me a moment. Okay, so then coming here, question 12, explain why it's necessary to check the short circuit current rating of the conductor in a feeder. Question 13, explain why the asymmetrical value of the current must be used to determine the short circuit current of the, okay. So then here the reason is that, remember, there is a transient. So whenever you hear asymmetric, so the long term current is like this, but the high term, remember, it's got a big transient. The transient here. So this is the AC metric, and this is the C metric. Okay, so then this AC can be as high as 1.7. Okay, so then that's the question 13 related to that. Then question 14, why it's important to calculate voltage drop? Well, imagine you have a long line of conductors, and then, for example, for lighting, for illumination, so all of these are lamps. They are in parallel. Okay, so we are going to have resistance, distributed resistance in the conductors. So imagine each lamp is taking 1 amp, 2 amps, 3 amps, 4 amps, 5 amps, 6, 7, 8. When we come here, we have 8 amps on the feeder. More lamps. When you come here, you are going to have 20 amps on the feeder. So now put the length here. Let's say, well, they can be long. Let's put half a mile. So if you start here with perhaps 277 volts, you need to end here 5% less. 277 times 0.95. No more than 5%. That's the rule. So what is that? $263 volts. Imagine in an airport runway. So here are the, and then here is the pilot coming. So let's draw here a plane. So the pilot is coming at, so the brightness of the lamp, that he uses to for distance. So then the voltage drop is important. And not only that, but also the connection. So in airport, serial connections. The lighting. So that the same current, so now the lamps are connected in series, not in parallel. So that the same current goes through each lamp, producing the same illumination. Okay, so that's just a curious special case of how airport runways have to be designed. Okay, fine. Okay, so then here we have maximum voltage. It says 11.3. It is very important, the correct voltage. The lamps are very sensitive to voltage. Okay, so then here is a rule. 3% for any branch circuit and 5% for all. So the 3% and 5% is this. So remember, we have our panels here. So these are the, okay, so then this is the feeder. Then here are the loads. So then this is the branch. So then what the book says, in the branch 3, all the way to the feeder 5. In the branch only 3%. Okay, including all the way to the feeder 5%. So then here is the reason why there is voltage drop. So here a very simple circuit, the load, the distributed resistance, the distributed reactance. It depends on the power factor. So here is the calculation of voltage drop. See, BS versus BL. So we have the source voltage and the load voltage. So then that difference is the voltage drop. So then here is the definition of voltage drop. Source minus load divided by source. So the voltage drop depends on the current, the length, the resistance, and the inductance, and the power factor. And then also depends on resistance, depends on conductor material, copper or aluminum, cross-sectional area, size, the temperature. The inductance depends on diameter, spacing, magnetic materials, the conduits, whether magnetic or not magnetic, and the frequency. Okay, so precise calculation. So the program that we have been using, the PTW32, calculates voltage drop. But here we will see these tables. Table, look. Okay. Fine. So then this is example. So then look at the example, 11.8. So 100% power factor, copper, magnetic conduit, voltage drop per 1000 ampere foot. So here they have this metric here, which is the ampere foot times 1000. So see, the first row in calculation is how many ampere feet. So that's 100 amps times 300 feet. So that's 30 ampere 1000 feet. So then with that 30 volts, go to table 11.5. So here is table 11.5. So copper, magnetic conduit, here. Magnetic are these columns are magnetic, look, okay? And then we have power factor, 80, 90, or 100. So in this case, it's 100. So we'll be using the last table right here. And then the size, this is what size? Number 2. So number 2 is right here. Okay, so the amount of 1000 ampere feet is 0.196. Okay. Now, for this case, the length multiplication by current is 30,000 ampere feet. So that's why in the second row of calculation, you can see 0.196 times 30. So therefore, the voltage drop is 5.88 volts. So this voltage is, it says is line to neutral. Line to line is 10.2 volts. And now it's going to compare with the voltage drop. So 10.2 is the voltage source minus voltage load. So divide 10.2 by the 480, which is the source. So then the percent is 2.1%. So then that's a good case. Okay. So now let's look at example 11.9. So now look, the voltage is lower. Now it's 208 volts. The current is 290 amps, so it's higher. The length is 150. The conductors are higher. Aluminum. So for this case, the ampere length is 290 times 150. So that's 43,500. So he's going to use 43.5. So now this is aluminum. The conductor is 250. So that's right here. The conduit is magnetic or non-magnetic. Aluminum conduit, non-magnetic. So that's on non-magnetic. It makes some difference, look. It does, less voltage drop. Not very much, but it does some. And then percent factor 90. So then we are right here. So 0.87 says 0.70. So I thought, why 70? Where is 70? I thought it was here. 200 low current, no, 3, 90 degrees. Okay, so there is a note there, note number 2. The correction factor for 90 centigrade is 1.1, 0.64 times 0.70. So here is the 0.64. That's for 400 kcm, not 250. Table 11, column 6, copper. Hold on. I thought it was aluminum. No, it's copper. So I'm wrong. I have to go copper here. Right here. Now I'm okay. 0.64. So then that gets multiplied by the amount of 1,000 ampere feet. 3 volts. Multiply by square root of 3, 5 volts. 5 divided by 208, 2.5%. So it's good. Okay. So then that's the case for voltage drop. Then there is questions regarding the conductors type, RHW, THW. So let me tell you where this is at. Letter designation of cables. Okay, so here is here. 259. So this topic are nice. Look here. Letter. So according to material, thermoplastic, cross-link, rubber, those are the most typical. According to conduction of use, H, heat, double H, 90 degrees, underground feeder, water, moisture resistance, So the most common, most cheap is thermo THW. Then the XHHW. So remember, THW, you cannot use it outdoors under the sun. Then other letters for other type of cable: armor cable, lead sheath, metal clad cable, non-metallic. So armor cables, they are used in very rough environments like factories or mines, where to protect the cable against being crushed by machines, moving machines. So that's okay. Then we have rifle. Okay. So then apart from this, there is another homework, which is these problems, the even problems. So let's quickly look at those. I will show it to you very fast. Hold on. And then we close. Assignments. Okay, so here we have. Here are the problems. Look, you see the problem 2, problem 4. Now, problem 6, it has A, B, C, D. So A is the first question. Percentage of voltage drop. Okay, so A is, so I put it step by step, so that first you calculate the current, then for B, you calculate the number of 1000 ampere feet. For C, you go to the table and calculate the line neutral voltage. For D, in percent. Okay, so that's problem 6. Then problem 8. So here is problem 8. Select the size of the conductors and conduit for feeder requirement following. Load is 80, 100% non-continuous, incandescent lighting, supply. So all this data, size of the conductor and conduit. So now conduit also, okay? So 8, it says, calculate the actual current. B, the conductor gauge. C, the asymmetric short circuit current in amps. D, the symmetric short circuit current in amps. E, answer to that question. So that's for short circuit. Then F, that's going to be for voltage drop. Okay, and then the last is select the size of the conductor. So that's the homework. So I could not. So then for homework, let me see if I have this. You see this, I could not put this on the homework, but I'm going to put this in course materials, okay? I'm going to put this image in course materials. It will not be in the homework. I'm sorry, but I tried and I could not do it. Okay, so then let's go. Let's come back. So let's say goodbye, and please put on your web cameras again.